Today we are going to discuss about analysis of first order RC high pass filter. As you know, the circuit diagram of RC high pass filter as capacitor is connected at the input side and output is taken across the resistor. First, we are analyzing the output voltage of the given RC circuit, that is high pass filter. Output voltage V0 equal to I current flowing through the circuit into resistance of that part. For output voltage is taken across resistance means the voltage at the output terminal Vout is measured as V0 equal to I into R by using Ohm's law. The input voltage Vin applied to the circuit is split across capacitor and resistance. So the total applied voltage Vin equal to I into R plus Xc. Voltage is equal to current into resistance. Resistance offered by the capacitance is called as capacitive reactance, and we have denoted this capacitive reactance as Xc. Xc is equal to 1 by j omega c. So the transfer function of the above circuit is V out by V in. So the V out by V out from equation 1, we get that V out equal to I into R and input voltage equal to I into R plus 1 by j omega c. So substitute equations input and output part in the transfer function or gain of the circuit. By solving the above equation, we will get V0 by V in equal to 1 divided by 1 plus 1 by j omega RC, where omega is the angular frequency, that is omega equal to 2 pi f. So output voltage by input voltage V0 by V in equal to 1 divided by 1 plus omega equal to 2 pi f into RC. So we know that the imaginary 1 by j is in equivalent to minus j. So the equation 4 can be rearranged and written as the gain function V0 by Vin equal to 1 divided by 1 minus j by 2 pi f RC. So let us assume that the cutoff frequency of the high pass filter as F1 or FH equal to 1 by 2 pi RC. As we know that the cutoff frequency of high pass filter is denoted by F1 or FL, that is equal to 1 by 2 pi RC. This equation becomes this part 1 by 2 pi RC is equal to F1. So we can rearrange equation 5 as V0 by V in equal to 1 upon 1 minus j F1 by F, where F1 or FL is the lower cutoff frequency of the high pass filter. In this expression, the denominator part constitute of the complex number, that is real plus imaginary term. So the magnitude of any complex number a plus or minus jb equal to square root of a square plus b square. By applying this magnitude function to analyze the gain of magnitude of gain, that's V0 by V in equal to 1 divided by square root of 1 plus f1 by f. Here in this term numerator term there is no imaginary part. So the square root of a plus 0b format is in the numerator part. So the magnitude becomes square root of 1, that is 1 itself. In the imaginary part, the magnitude becomes square root of 1 square plus square root of JB. B term here is F1 by F. So the magnitude becomes F1 by F whole square. So the magnitude expression for high pass filter, we got it as V0 by Vin equal to 1 divided by square root of F1 by F whole square. We can analyze this expression at 3 frequency cases. At frequency equal to 0, that is f equal to 0, what will be the gain? And at f equal to f1 or fl, that is in the case of high pass filter, we can represent the cutoff frequency as f1 or fl. At that time, what will be the gain? At f equal to infinity, what will be the gain? At three cases, we are analyzing the gain function of high pass filter. At f equal to 0, the gain becomes, by applying f equal to 0, that is 1 plus 1 by infinity, 1 by infinity, 1 by 0 means infinity, 1 plus infinity becomes infinity. So at f equal to 0, the gain becomes 0. At f equal to f1, by substituting f equal to f1, at the denominator part becomes 1 by square root of 1 plus 1 by 1 square means 1. 1 plus 1 means 2. At f equal to f1, at cutoff frequency, the gain becomes 1 by root 2. At f equal to infinity, the gain becomes 1 by 1, that is unity. By analyzing these 3 points, we can draw the frequency response curve of high pass filters as shown in figure. As along x-axis we are taking the frequency, and along y-axis we are taking the gain component. V0 by Vin is plotted across y-axis, and in x-axis we are taking the frequency. At frequency becomes 0, the gain becomes, at f equal to 0, the gain becomes 0. So we are getting the response at f equal to 0, gain is 0. At f equal to f1, that is at cutoff frequency, gain becomes 1 by root 2 times. F increases means f tends to infinity, gain becomes unity. This is the frequency response plot of high pass filter. Low frequency band is attenuated and high frequency signals are passed using high pass filter. When we are analyzing the phase angle curve, phase angle is given by tan inverse B by A. An imaginary this numerator part doesn't have any imaginary component. So tan inverse 0 minus tan inverse, here B is minus f1 by f. Substituting the imaginary term, we are getting the phase angle as tan inverse f1 by f. At the same scenario, we can analyze the phase angle in 3 frequency components. That is, when f becomes 0, f becomes f1, when f becomes infinity. When f equal to 0, the phase angle of high pass filter become 90 degree. When f equal to, at the cutoff frequency, phase angle we are getting as 45 degree, and f equal to infinity, the phase angle we are getting as 0 degree. This is the phase response of high pass filter, first order high pass filter. In this same scenario, we can analyze the low pass filter also. In the case of low pass filter, the resistor is connected at the input side and capacitor is connected at the output side. The frequency response curve of low pass filter can be analyzed in the same manner. Frequency curve of low. First, we have to find the output voltage. Output voltage of the circuit is current into, that is capacity reactance, that is XC, and the input voltage Vin equal to I into R plus JXC. R plus I into JXC. By analyzing the equation 2 and 1, we have to find out the gain of the circuit, that is V0 by Vin equal to output voltage equal to I into Xc and input voltage equal to I into R plus Xc. So substituting the Xc component, that is 1 by j omega c, we are getting V0 by Vin as I by j omega c. At the input side, I into R plus 1 by j omega c. By solving this equation, we are getting the gain expression of low pass filter as 1 divided by j omega RC plus 1, that is equal to 1 divided by 1 plus j omega RC. Here also the omega is the angular frequency, omega equal to 2 pi f. So gain becomes V0 by Vin equal to 1 divided by 1 plus j 2 pi f RC. We know that the cutoff frequency of, we already expressed the cutoff frequency of low pass filter as F1, high pass filter as F1 or FH. In the same scenario, we can represent the cutoff frequency of low pass filter as F2, or abbreviation we are using as FH, that is equal to 1 by 2 pi RC. That is substituted back here. So we are getting the gain expression. 2 pi RC means 1 divided by F2. So the expression becomes V0 by Vn equal to 1 divided by 1 plus Jf by F2. In the same case, we are analyzing at the when frequency becomes 0, what will be the gain? Frequency become at the cutoff frequency, what will be the gain? At frequency tends to infinity, what will be the gain? At 3 scenario, we are finding the gain as at frequency becomes 0 by finding the magnitude of gain. We are getting gain as 1. 1 plus f equal to 0 divided by f2 means 0 divided by f2 means 0. 1 by 1 means 1. F equal to f2 means 1 by 1 plus 1, that is 1 by 1 plus square root of 1 plus 1 means square root of 2. At f equal to infinity means 1 plus infinity, that is infinity. 1 divided by infinity becomes 0. So the gain becomes at f equal to 0, 1, f equal to cutoff frequency f2 or fh, the gain becomes 1 by root 2. F tends to infinity, the gain becomes 0. So we are getting the frequency response of low pass filter. Low frequency components are passed and high frequency components are attenuated. In normal scenario, we normally plot the frequency response plot in logarithmic scale. So we are using log f along x-axis and gain in dB along y-axis. This is the frequency response drawn in logarithmic scale. The log of 1 is 0 dB. From that, minus 3 dB down response plot made the point is known as cutoff frequency. So we are analyzed the first order high pass filter and first order low pass filter and the response curve of both first order and second order low pass filter.